All right, so this week we're going to talk about mechanisms, which is just a continuation of building a machine. And so we've definitely been hitting those strides. This is our third set of notes that have to do with machines. What we want to do is continue on with sort of our pyramid of what it takes to build a machine. We've got the active components. Everybody's been sort of wrestling with their active components. There's a physical structure. Yesterday there was a lot of physical structure done on the Sandify CNC. Then there's the code base. So there's those three pieces that we're going to take a look at to try and address what's going on with each of them. So we're going to hit these topics. We're going to talk about feedback loops in general, different ways that you can get feedback loops, which includes end stops. That's a big one. Almost all of the, well, all the 3D printers have them. And then we're going to look at other places where they exist and sort of the rules around them. We'll identify a motion encoder for a machine like we'd be dealing with. And then we'll talk about conceptually end effector feedback. Then we'll identify GRBL and Marlin. And then maybe, fingers crossed, one of you will upload Marlin onto an Arduino today. And then we'll talk about control systems in general, because that is its own entire field of engineering, in case you were curious. And then we'll talk a little bit just sort of conceptually about startup calibration just as a concept and its fit into things. So first off, we're still talking about active components. They definitely take the most focus in doing all of this. But essentially here, we're talking about the inputs on the machine. So we talked about inputs and outputs in the past, but these are inputs that you bake into it so that it gets feedback about itself. If you just tell the motors to move, they can totally, but they have no self-awareness. There's no feedback. There's no system where they know where they are, where they're moving. All of that is just blind on most simple robots. And so it's just going into the darkness. But you can add inputs so that it has some orientation, some place where it understands what's going on. And so the very simplest of those are end stops. End stops can look a lot like this over here on the right. They're the simplest thing. It's just a button inside the machine so that when it moves, it presses a button. That's it. That's the entire concept. They're really, really useful to set origin positions. And so on the CNC linear axis that is right in front of Lila, there's an end stop button on the one end. And all it does is that when the carriage moves along that axis, at some point it reaches an edge. And when it hits that edge, that's got an end stop button, and it presses that button and it can recognize that to know that it's hit one of its limits, rather than just moving back and forth in the dark. Even larger machines like the Gerber will have end stops that are true end stops, soft end stops, where when it hits the end of the range that it can travel, before it crashes into something, they put a switch just inside of there so that it can press that switch and realize like, oh, I'm not allowed to go further than this, and it will stop the motors rather than crashing into the actual like hard edge of the machine. And then there's homing end stops. There's a lot of ways that you could use these, but they are buttons that you apply so that you can move. And so here's a little tiny picture of a timing belt axis where you've got this hot end here that moves along. And right where I put this pink triangle thing, that could be a position for an end stop. And when I power this up, that nozzle may start in any random position. But if I have it slowly, slowly, slowly go this way, and each time it makes a step, it checks to see if the button's been pressed. As soon as that button gets pressed, it knows where it is and it can stop moving in the direction towards the button. That sets an origin location along that axis, and I can know where that start point is. So even though it starts wherever the print ended, I can know where it is at the beginning by finding the end stops as the first thing. And if you watch the Prusa and you sort of hit the go button and you just watch what happens, baked into the slicers that we have on Octopi, it always does a homing sequence. So it'll always slowly go and find the end stops, and you'll hear the click, and then usually it backs off and does a click again. And then it'll do that for each one of the three axes so that it can find all of those home positions. Ruby, did you have a question?
Yeah, does the Gerber have this, and if it doesn't, could it?
So the Gerber has end stops. It has soft end stops so that it won't crash into itself. And then Lior and I bought a button so that the end mill will one day, when all of the stars align, you'll have this button that exists, and it'll take your end mill that's loaded. It has a tool changer and everything. It'll come down and press the button so that it knows right where the end of the tool is. And so one day that will be the way that we get it to 0. And that button is on a very long cord. So you could set it on top of the workpiece. to be referenced to the top of the workpiece. You could set it on the machine bed so that you reference there, or you could set it like in a fixed position if you want to know the tool offset. And there's a few ways to use buttons like that, but they're really, really helpful. Most 3D printers, because you're not talking about the amount of force of the Gerber, it will zero and home normally. And if they run into the end, it's not that big of a deal. It doesn't hurt anything. The Gerber has the soft end stops because if it's running full force into the side, it can do some self-damage. The same is true for the Tormach. It's got soft end stops, so it will not drive all the way into the side. Any very high-end CNC is going to have those. And so those are useful. These are sort of I think that's an image from buying them in bulk, where you buy these and you put them on a 3D printer. So this is definitely a way to do it. There's lots of different ways that you can do this to make your machine progressively safer and safer with the more of these that you include, because basically it'll just follow the stepper motor guidance, even if you tell it to move 14 feet to the left, right? It may not have 14 feet of travel, but it can follow those instructions and just go and go and go. An end stop would keep it from hitting its own edges. So that can be really helpful. What's up?
You say when the stars align.
What does it mean when I say when the stars align? To have the button added to the Gerber. The short answer is that we need to find a time where Lior and I can both be staring at it to plug it into the right spot and get the wires run inside the Gerber and put code into Linux CNC. So we need to code and wire and do those things to really we're actually modifying the Gerber when we install that. So we need to have like a dedicated several hours where we're able to figure that out. And so, that might be a thing that I work on after foundations, right? But it's just going to take some time to figure out how to integrate it into the machine and not change the user experience almost at all. But it's really helpful. There's also multiple different ways to do this. The button is the easiest way. And so these little roller buttons are really common, especially with the wheel on the end. That way, it doesn't matter too much where it's hit from. It can handle it just fine. But this is an optical end stop. And this is actually the kind that's on the Gerber. They have optical end stops instead of hard end stops, the button style, where there's a little fin that sort of moves along. And when the finger or that fin blocks in between those two verticals, then it can't send a beam back and forth. And it knows, oh, there's something here. And it stops. These are good. Those are really good for soft end stops when you don't want to have a thing hit a button. And the Gerber's a good example because that fin, if it doesn't have a wall that's about just on the other side of that, if it overshoots by an inch because it was moving super fast, that's actually going to be fine. It'll still be able to go. A soft end stop with optical sensor is a safe way to go on a machine that's that big that can move that fast. Another thing that's good on a machine like the Gerber, a big one with lots of metal pieces, is one of these proximity switches. This little blue tip over here has sort of a, I'm going to say metal detector, even though that's not quite right. But it's got a metal detector, so it can sense that when a metal piece comes right in front of it, oh, there's the end of the range, and I can stop there. It's a little beefier than a button. The reason why the Gerber wouldn't use these is because they're small and plastic, and if they get hit just wrong, they break, right? And so you want to have more robust solutions for larger, more aggressive things. But in any case, these all would work the same. It's essentially a button or a sensor that tells you where the edge of your motion is. And so that's really helpful. We're definitely working on automated zeroing though for the Gerber because it will make the whole machine safer when we get that up and running. Whoops. And so that is just all you get when you have an end stop is you know that you're at the end. But then once you leave the end, you're just promising that all your steps work just right, and that's all you know. The next step is to add encoders to motors. And so if you have a machine where you really want to be certain that it's at the place where it says it is, you can measure that motion with encoders. And so we've played with encoders a little bit. They were on that Arduino Shield, and you can use them as like the volume knob on a car stereo where you can just crank the knob or spin it continuously. If you attach that to a motor, whether it's on the back end here or there's some other mechanisms you can do, an encoder will be able to track the motion of a motor overall, which is really helpful. That way it can keep track of how far it's spun and what direction it's spun so that you can be conscious of the movement that has actually happened relative to what you told it to do. So if you incorporate encoders, then you can verify the distance that you've traveled. 3D printers don't often have these because they're just, relatively low risk. If it doesn't make the steps, the print fails, you try again, you're out $10 at most, right? But on something like the Gerber or the Tormach, some industrial CNC machine where you could be wasting lots and lots of money and you want to keep an eye on the health of your machine, encoders can be really helpful. They come in all sorts of scales and sizes. There's these ones which have little magnetic sensors on this one and this one and this one. They have little magnets that spin on the back end of the motor shaft, and when that spins, they have the Hall sensors that can tell that the magnet's rotated, and they use that to tell it's gone. Some of them are really charmingly optical. Like they have a little slotted wheel, and that little slotted wheel, when it sees the slots go by, it's able to track what's going on in sort of this spinny diagram kind of way. There's some mechanisms to that are still interesting. This is a really high-end encoder. It looks like a motor, but it's actually just an input so that it can track its motion. Something like this might have, does it have it? This might be 600 steps per rotation. So this looks like it's 6 steps per rotation, and you can buy like the little cheap ones that you get on or for like a volume knob. They might have 24 steps per rotation. Something like this would be maybe 600, right? And if you do gearing, you can get even more precise, but these are really interesting. One, and I've used these before. I had students that were building cars that needed to drive a certain distance autonomously and stop right on the target. And so we talked a lot about how you use an encoder for that, because you could put it right on the drive wheel. And once the drive wheel had turned just enough, it would stop. And that seemed like it would be a really good choice, except you have the problem of slippage with encoders also. And it's a minor problem, but if your wheels, if you imagine a drag racer, its wheels spin really fast. And if you look at a high speed photo, they'll even like twist the wheels and they'll slip against the pavement. That's why you get burnout. Sometimes you take an encoder in a critical situation and you want to move it off of the motor so that if the motor slips, your encoder is measuring what you really care about spinning. So in the case of those kids' cars, we didn't put it on the drive axle, we put it on the passive axle. So it didn't matter how much the motor spun or how much the motor slipped. It was watching the wheel that wasn't being driven that would never slip. It was just riding across the ground. So there's some interesting dynamics to using encoders if you want to get very high accuracy. But in that case of a high schooler project car, they were able to measure their distance traveled to, I think it was 10 micrometers because of the gearing ratio and the high-end encoder that we had bought for it. It was pretty ridiculous. They could hit their target very on point. They actually had, they could measure so well that they had to sacrifice a little bit because the motor wasn't as accurate as their measurements. Encoders can be really, really helpful. They're also often not something you have to play with. Oh, the banana is just like, it's this weird company, Tropical Labs. This is a fun little package for like $12. You can put that on the back of a stepper. An industrial servo is a encoder slapped on the back of a stepper motor. Because you've got this, and this is an industrial servo over here. It's essentially a giant stepper motor, and on the back, there's some encoder stuff. This is an attempt to make a very cheap version of the same thing. So if you have a stepper that you like, you can add encoders just to verify that it's working exactly how you want. And then the bananas has nothing to do with it whatsoever, but it's a, you know.
Perhaps for scale.
I think for scale, maybe. Yeah, just banana for scale. I guess that's it. You can put encoders on most. Yeah, it's a bad for scale. There's a, it's a mini banana. But it could. Yeah, it could be what it, you know. It's good for. One more thing. If you're putting these onto motors, you'll also need to use probably interrupts in Arduino because they're spinning so fast that you have to interrupt the program each time a step happens. And that's not true if you're using it as a controller knob where you're turning it by hand, but if a motor is spinning it, it'll often spin faster than it can measure, which is interesting. Okay, and then the last type of feedback, all of these are just focused on machines knowing how they're operating. So the end stops gave it an origin point, the encoders can track the motion overall, and then a lot of the time you need an end effector feedback system. And there's no one good solution for this because each end effector is different. I just threw in that slide from the last week because there's a lot of variety in end effectors. And so if it's a hot end, you'll need to measure temperature. If you're doling out electricity, you might monitor the current draw of a motor to see if you've stalled your end mill motor. You could be measuring the rotation with a tachyometer sort of thing to see how much your end mill is spinning or the speed of its rotation to tell if it speeds up or slows down. There's a lot of different things that you might do to measure how something has worked. Maybe you measure the smell quality of your pancake if you've got that pancake bot. I don't know, probably not. But the key is that you'll probably need some unique solution. But in any case, you have to think about what's the critical property that you're playing with, and then how do you measure it in such a way that you can give feedback in a meaningful way. The hot end on a 3D printer is a great example because you have a heater that basically just lives in two states. It's either on and warming up, or it's off and cooling down. And so you need a thermometer to tell you, should it be on or should it be off? Are you above or below the mark? Right? And so having feedback that meaningfully connects the heater and the temperature is the important part there. So you'll have to be a little conscious about how it is you want to do that. And you don't always need end effector feedback, but usually on a larger machine or on something that heats up and could potentially be a fire risk, like a 3D printer, you absolutely want to think about it. So those are sorts of things that we need to keep a close eye on if you're building something. In the case of our garden CNC, there really doesn't need to be much feedback. It's just a magnet, and the magnet's going to do what the magnet does. You could potentially, maybe we put a magnet Hall sensor there, a magnet sensor. And if the Hall sensor all of a sudden doesn't sense a magnet, we can know something catastrophic happened, right? The magnet disappeared, it fell off, it's gone. You might do something as easy as that, just as a cutoff, a system shut off would be that sort of a thing. We talked about the importance of those last week. It's definitely true, and end effector feedback can be a good case for that sort of a thing. But then how do you think about that? How do you integrate? These are sensing things. Now you start to think about, how do you code that? How does it build into the way that the system operates? And there's going to be some logic that has to work with this, but we're going to start to look at different packaged pieces. So for a lot of machines, if you're building something that's going to follow G code, you're going to want to have a firmware system. And so Marlin and GRBL are two really popular, famous firmware systems. Marlin is almost universal. Marlin is the firmware, the software, the Arduino program that you load onto the Arduino that runs the 3D printer. So Marlin is the Arduino sketch, essentially. It's a really big, ornate Arduino sketch that you load onto the Arduino that runs the 3D printer. And that's all the firmware is. Sometimes people get locked up on firmware. They think it's something else, but it's really just genuinely an Arduino sketch. But usually something like Marlin is thousands of lines of code. It's got lots of variables and things and pieces to tweak. And a 3D printer company might hire an engineer to manage their specific installation of Marlin on their 3D printing machines. I've known an engineer who did specifically that for a 3D printing company back in Cleveland. What's up?
So does that mean that I could go into a 3D printer and discover / pull out Marlin code?
I have 100% done that, and it works great. I did it for my Tempe incubator. I pulled out the Marlin firmware bed control temperature curves. So you can, if you can get access to their version of the firmware, you can totally play with it, tinker with it, and dial in those settings. People who are very deep in the weeds on their own 3D printers will certainly go in and tweak their firmware. And you can totally do that. And usually, like, the quality of the printer, there's like the mechanical pieces that make a 3D printer better, but a relatively cheap way to make cheap parts a better printer is to have really well-tuned firmware. And alternatively, even putting in the best parts into a 3D printer, if your firmware kind of sucks, then it's not going to be, if your settings on firmware aren't that great, you can have a bad 3D printer for that reason. GRBL is neat because a GRBL firmware will just run with easel from Inventables. So if you have a CNC that you've built and it's got GRBL firmware on it, it's just one of the options in easel for the Shipoko. Instead of printing to a Shipoko, or I think there's a couple other bots that are made by Inventables, one of their options is Arduino board with GRBL. And so you can just print directly to any GRBL firmware Arduino board. And so that's another famous one just for that purpose. Generally, I've seen this one for CNCs and Marlin more often for 3D printers. You can certainly write your own, but because it's a very large investment to really build this up from scratch, a lot of the times people, even companies, will use derivatives of these two. So like Maker Gear, which it makes 3D printers that I really enjoy, those 3D printers use a flavor of Marlin where they've tweaked it and you can download their firmware and open it in Arduino if you'd like. Yeah.
I'm still trying to kind of compile this in my brain.
Sure.
So in our example, in the sand table, is it that we have, like, where Sandify makes this G code?
Yes.
But then the Marlin is what is going to read that G code and translate it into movement?
Yes, and so that's a really good question. The G code that you get out of Sandify tells it how to move, but it's not going to know everything about your machine. That Sandify G code could, in theory, be done on any of the 15 sand machines we have in an imaginary world, and the firmware would say this is how you're going to run it here. Like a good example is that there's some variables that get stored in your firmware, like how many steps of the stepper motor does it take to move 1 inch is an important question. And that's a question that would be answered by a variable that's in your firmware. So the firmware of the machine would know, oh, I need to move exactly 1,352 steps to go 1 inch. And so then when you give it G code that says move 1.5 inches, the firmware interprets that, takes its steps per inch, and translates it into a specific action that the motor has to take. So it definitely takes the instructions of the G code, turns it into motor actions, and that sort of goes in between. But the G code file is loaded by the firmware, the program on Arduino. The Arduino pulls open that file and just sort of reads it line by line, inserting the variables and controls that it needs. Yeah, no, it's a little wonky. But in Arduino, if you think about the Arduino as a tiny computer, it's got a program running on it. That's the firmware. And that program can open a file, the G code file, and read it. And as it's reading it, it needs to interpret a few things. Like if it says to travel 1 inch, the program running it will interpret that go 1 inch command and say, okay, now I need to move exactly this many steps on the motor to follow that instruction. Let's imagine you want to draw a 3-inch circle, right? And you want a robot, you want 2 different robots to cut a 3-inch circle, the Shipoko and the Gerber. That G code command for cut a 3-inch circle is fundamentally the same. It's just the please draw a 3-inch circle. And the firmware on the Shipoko will make that happen for the amount of steps it takes on those motors, which are lower quality. And it'll take more steps on the Gerber because there's higher resolution. And so the firmware decides how many real motor steps do I have to make in order to get my gearing and motors and all of that to do the 3-inch circle. That's one piece. So one set of G code can run on multiple machines. The other part of your question, we need to have G code separate from firmware because on a 3D printer is a good example. I can use the same machine and it follows different G code controls to do many different prints. If I wrote the operation all into the firmware, then it would just be press this button and it prints the same thing each time. By loading a G code file, I can have the same sort of framework of move motors, find end stops, heat up the bed, run any different G code file that I want. So I can load in the file for a tiny Pikachu. I can load in the file for some bracket. I can load in a file for a planter. And the G code file changes, but all the steps per inch and all of the end stop finding and heating and cooling, those pieces are all consistent every time the machine operates. But I load a different file and it moves in different directions to make those different objects.
So if you were like
We're having a good discussion
writing
about
the
the firmware is really important to get. The firmware is really important so that the G code, which stores information about shapes and geometry and those sorts of things and motions of the end mills on a CNC, the G code stores that information and the firmware stores all the information that translates from the motion, the like gross motions, into the fine stepped. To move 1 inch takes 1,500 steps of the motor on this machine, and on another machine it might take 1,400, and it can deal with all those little idiosyncrasies. Yeah, so it's good. I'm going to repeat that one, and then I think we move on. That was a really good line, Ruby. You're good at you hit those lines spot on. The G code is your design, and the firmware is how that design comes into reality. And each machine will be a little different in how it brings it into reality, but the design might be the same across different machines. Also, it means that the same machine with just the mechanisms that it has can load different designs and run different designs. It's sort of a two-way street in that it separates out the designs and how you make things in a really useful way. But that said, one of the things that's baked into firmware and lots of other pieces are control systems. And this is something that I want to make sure that we get to. We can talk about firmware a lot at length for sure, but the control systems are something that you'd include in those. And control systems engineering is its entire own whole field of engineering. And it's all about measuring some property, finding the error that you have between what you want it to be and what you really have, and then closing that error gap as much as you possibly can. This diagram is sort of a generic thing that if you have some disturbance, something happens, that's an input, you'll measure an element, you'll get some observed value. You'll have a set point, like maybe you observe the temperature of the bed on your printer to be 58 degrees. Your set point is that you'd like it to be 60 degrees Celsius. And so there's an error of 2 degrees. You're 2 degrees too low compared to the temperature that you want. So then that will set a command that'll go back to the effector and say, I want you to warm up until you get 2 degrees warmer. So there's a whole feedback loop that goes into control systems where you're measuring some status of the machine. You have an idea of what you'd like it to be. You find the difference between those, and then you use that as a feedback loop to get back. This may sound relatively complicated and straightforward all at the same time. This is a weird thing. But we're going to look at 2 types of control that may have it make more sense. This is just the diagram to get ourselves started. But the big thing is that you want to think about those 3 items. Your set point, which is what you'd like it to be, the value, which is what it is, and then the error, which is the subtracted difference between those 2. So if you'd like it to be, and keep that in mind, that example in mind, if you'd like it to be 60 degrees on a heated bed, and it's really 58, your error is 2 degrees too cold, and then you give some command that says warm up, right? And so there's some mechanisms into how that all works that are worth looking into. So bang bang control is a real name for a type of control system. And essentially, for a heated bed, for a heater, you have a thermometer that measures, is it too cold? This is what your furnace does, essentially. If it's too cold, turn on the burner. It'll warm up. And then if it's warm enough, turn off, and it'll slowly cool back down. Once it gets too cold again, it turns the burner back on and it warms back up. Right? A thermostat is exactly a bang bang controller, where if the temperature is too low, turn on the furnace, it'll heat up. And then once it's too high, it'll power off the furnace, or after a certain amount of time, it'll power off the furnace, and then it'll cool back down. So you've got this really sort of, if you would like your room to be lighter than it is, you turn on the light. If you'd like it to be darker than it is, you turn off the light. Flappy Bird is a good example, actually, of bang bang control. You press the screen and the bird gets higher. You let up on the screen and the bird gets lower, and you want the bird to go between pipes. Like, this is something that is such a simple part of how control and feedback loop systems work that we actually turn it into games pretty regularly. It's an interesting piece. It's essentially just a negative feedback loop where if you're too warm, you cool off, and if you're too cold, you heat up. Or if you're spinning too fast, you'll slow the power down on the motor, and if you're spinning too slow, you'll up the power on the motor. Right? There's a whole host of this, but you want to start off with some stimulus that you need to sense, and then you'll evaluate, are we doing better or worse than we'd like? And then that'll have the effector that will change your stimulus again, so that you have this closed loop where you're able to observe what's going on and respond to it so that you can stay on a target. Always thinking about your set point, the value that you observe, and then the error from there so that you can balance this into where you want to be. So bang bang control, like in this case, here's an oscilloscope, and I think this is just a standard square wave. But let's say you wanted to be in the middle line right here. If I'm too low, it'll turn on the engine and it'll go above. And then at some point here, it realizes, oh, that's too high. And then it turns off. And when it drops down below and it realizes it, it'll turn back on and go back up and then off and back on. It's just sort of a on, off, on, off, on, off to stay at around a stable point. So that's really all bang bang control is. It's just turn it all the way on or turn it all the way off, and that's it. And that works pretty well in a lot of scenarios. It's not terribly hard to control. It's read a sensor, and then it's if then logic. So if it's too cold, warm, and if it's too warm, cold. It's a nice simple one to code, and it can do a great job. PID control, which is proportional, integral, and derivative, is a really interesting one. This is a control system that is, this is probably its own entire college course in and of itself. But it's got a really good use of some fairly complicated math, the calculus, which you might remember from, maybe you remember that trauma from college. The calculus that goes along here, there's different ways to think about how a value changes over time or how a line changes over time. And so you can think about its value by looking at the actual value of a trend, the number that it represents. You can think about the slope of a line at a given point, or you can think about how far off it is from a target at a given point. And so by interpreting those three things and fine tuning exactly how you want it to work, Bang Bang can do a great job at dialing in control, but PID turns out it can be even better. So this is an interesting graph that sort of looks at how a 3D printer heated bed might change over time. This is essentially just bang bang control. You'll notice that it goes up, it's heating and heating and heating, and it overshoots. And then it turns it off, so it cools down and it goes way too low, and then it turns on and it goes way too high, and it goes up and down over the temperature. For early on, PID and bang bang look similar in that they sort of ping pong up and down over a set point. The red line is the set point in this particular image. What PID control has going for it is that it takes into account a few different things, and critically, how far off target it has been over the last little while and how quickly is it approaching the target set point. And if you dial in these three variables that have to do with the proportional, integral, and derivative or differential difference here, you can really get a PID control to really quickly approach your set point and then stabilize right on it and hold that set point really, really stable. So this is what almost all 3D printers use for their heated nozzles, their heated beds. It's what lots of systems will use. And this has become so commonplace because it's so good at controlling things that there's often a software package where you just say, I would like to do PID control. And there's usually even an auto tuning feature for PID. So it'll automatically set those three critical values. And then those three variables, the ones that are sort of being manipulated over here, it goes through and messes with in this example, it plays with the P, the I, and the D values separately. So you can watch it sort of adjust those and what the behavior would be. These values, when it gets to the perfect setup, it would store them in the firmware, just like the steps per inch would be stored in firmware. So when you have the three perfect values for your heated bed, for your temperature sensor, and your setup, you can eventually save all of those in your firmware and it'll work just fine. But it's a complicated one to wrap your head around, and the odds are is you won't be coding that yourself. But what it really does nicely is PID has really good control. If you have you might have seen robots or Segways. A Segway has two wheels on a single axle and it should not stand upright. But a Segway uses PID control and a 9 degree of freedom sensor or 6 degree of freedom sensor to be able to tell if it's falling over, right? And so a Segway can stand upright on two wheels because it can tell if it's even moving just slightly off from over top of those two wheels, and the PID will move the wheels underneath where it's falling towards. So it can stand upright on two wheels itself. And so that works perfectly fine for one of these goofy telepresence things that I hope someone got to experience during the pandemic, where it's like your head on an iPad and then you're rolling around on these little wheels. Those are pretty ridiculous things, but PID control keeps these things upright, otherwise they'd fall over. The same is true for BB-8. BB-8, the drone, is totally PID controlled. They've made plenty of hardware versions where the head stays up on top for a number of ways, but PID control can do that. And then you can absolutely get an Arduino with a couple of motors and wheels mounted on it. And if it's got the right sensor, you can use PID control to make an Arduino robot that stands upright. For all of the crazy, creepy dancing robots that Boston Dynamic puts out, anything that can stand sort of upright instead of on 3 or 4 legs, it's using some version of PID control to keep its balance. So PID is really good at holding a temperature, holding a position, holding something very steady. It's absolutely what needs to happen. The drone that flew on Mars not that long ago for the very first time, it was absolutely held stable by PID control. As it would have tipped just a little bit off axis, it needed to do those calculations exceptionally fast so that it would be more stable and a person could hold it. What's up?
Is this used at all in like prosthetic limbs? with
It-
like balance control?
PID is all over the place. This is super, super common. And it's definitely worth like nerding out on for a while if you really wanted to get all the logistics. It's also, it gets pretty deep pretty quickly, but you should 100% know the name. The variables are almost always marked KP, KI, and KB. And you can sort of tune those and tweak those so that they're perfect for your particular 3D printer or your particular CNC or prosthetic arm or any of those things. So these are all variables that really can stabilize systems so they work just right.
What does it stand for again?
Proportional, integral, and differential. Because it's the direct, like that, the direct relationship is the proportional. The integral is actually measuring on this graphic. The integral is measuring how much space there is between the line and the set point. So like how far off target you are over time. And then the derivative is measuring what's the slope of this line. So like right now it's really steep and it's like headed not in the same direction as the red line. When you crank up the D, see how it gets flatter and closer to the set point line, which is horizontal. It gets more horizontal as you fiddle with your KB. So it's a really interesting calculus investigation that we don't need to go into now, but it is also interesting if you're, and I feel like they should teach this in high school and college calculus because it's actually an application. There's a lot of kids that ask, why are we doing this math? This would be a good excuse to like really sell it if they went into it. And then the last piece, and this is pretty quick, I want to stop fairly soon, is machine setup. So we talked about end stops and PID control. Most machines, we should start a 3D print right after we're done here, just so that you can look at it, do all of its startup things. Most machines will have a startup sequence. And my guess is that into both of our solutions, there's going to be some sort of a power up routine where it finds its home, it moves to the center of the circle on Sandify, it like primes all the pumps just right, it does some actions. One of the important things that you're going to want to think about is how do you do that? And in Octopi or in Sandify, there's usually a space where you can input a few lines of G code at the beginning and a few lines of G code at the end of any G code that you generate about your design, so that those sorts of actions can happen if you want them. Not everybody needs them, and sometimes some printers, some 3D printers have like suggested G code you put at the beginning and end, and others are kind of lax about it. But it's an interesting piece to think about how this works. But definitely you can see this in action if we just start a 3D print on the Prusa. So I think that's a good one to watch happen. And you can see that it will set itself up by finding its home positions and then just setting the temperature, and it will pause and wait until the PID control has gotten the bed and the nozzle to the temperatures that you want, which is really like once you put that into context that it's getting set up, it's finding all those homes. It's fascinating to think about all those pieces and how they fit together. But for the sake of thinking about the Gerber again, here are 3 end stops. D and A, those are the soft end stops that would be on either side. And this is actually an image taken from Linux CNC. Those switches are there so that the green guy here that moves back and forth doesn't slam into the gray blocks on the sides. So you put soft end stops so that it stops in software before it slams into this thing over here. And then in some machines, they'll have a separate other origin point, which is not one of the soft end stops. It's set in a little bit so that it's not the same duty. On a 3D printer, those are usually one button and it does both jobs with the same button. So it depends on the fidelity of your machine and how you want to tune it. But you can have homing switches that are separate from end stops, and those can be tuned a number of different ways. But usually at the end of a G code, you'll have some random position where it stops, and you'll want to go through some routine so you can find your origin before it gets started with the next design. What's up? a post processor essentially does a lot of the work for get all my settings just right for this,
For the firmware.
for the G code and firmware to be married well, right? You can Sandify exports G code that's just the design, has almost no post processing. We'd sort of manually add in the post processing, which is if you want to put in a command that says go find your home before the design or go to the center of the circle after the design, those are the sorts of things that post processing can do. It can do other stuff, but that's like the final closing the loop on your G code beyond just the design itself. Yeah, that's what the post processing is all about. Which is interesting. So choosing the right post processor gets the G code to work with the firmware and the two to work as expected with each other. And so like an example is the Gerber, it inputs a G64 or a G61 depending on the post processor you want, and that sets some settings because the Gerber could go either way. You can
I guess I'm wondering, is post-processor?
It's a post processor in some design software like in Fusion 360. When you have the CAM that you do in Fusion 360, you've designed your thing. The CAM is how do you want to machine it, and then the last step before you click export, so you can load it into the Gerber, you have to select a post processor that basically says I'm exporting this G code for this machine. Give it the right line, the right 3 lines at the beginning and 1 line at the end in the G code for the machine where I'm sending it. So it's like the in-between from the design geometry shape to the machine. There's like if you need an extra step, the post processor can help you get that all set up just right.
Is that
Actually that. Different firmwares do different things. Some Gerber handles a little bit more in the G code and Marlin handles a little bit more in the firmware. And there are differences that are entirely like just arbitrary choices. But that is the end of what I wanted to get through, which is kind of a lot. But I wanted to make sure that we had a little bit of extra time to talk about final projects, to think about some of those thoughts. And also just to say, like, we're still going on group projects. We're at the halfway point for time, which is exciting and a little scary all at once. This is week 3 of 4 on group project dedicated time. And so we have this week until next Monday, and then the week after that. So 14 days worth of time to work on these machines. And then we should have a show and tell that says, yes, group projects are done. Now it's time for individual projects. Although you can start to make that transition at any point when your group is done or if you have free time. So show and tell we can do about what we've been up to. And it hurts me to not really have a show and tell. If Liana was on, I would love to share those pictures. She put them in Slack. We should all go Google them. She did a great job putting that mural up. So if she's watching this later, great job on the mural. And if we did other cool stuff, we should absolutely chat about that. But the final projects are worth talking about for a minute. Final projects, we're still ahead of time. We're going to talk about those a little bit more as we get closer. But you should definitely be thinking about what you want to do. I want to put some parameters on what it should be and what it shouldn't be, and then we can try and finalize details further. They should be a way for you to showcase your best skills, right? To say, these are the cool things that I've learned in the class. This is my personality made manifest in a thing that I've made. And here is all of that coolness all in one shot. That said, you can immediately say like, oh, I want to build this cool thing. I want to put it on Mars. It's going to send me back signals because I'm that cool. Like you can dream up something that's really huge really quickly. So there's parameters on it too. One, it should not touch every one of our units. You'll drive yourself mad if you try and do that. Maximum, I would say, is half of our units. Maximum you should shoot for is even touching half of our units. But it should try and integrate several. So more than just one thing, more than a couple things. It'd be great if it hit onto multiple areas that we've covered. And the other thing is that you've got a time limit. So in here, we've been doing spiral design for group projects, and the SAN CNC has done a really good job of, there was the first version, there's the second version, and now they're going on to the third version, which is really going well. The garden team is doing some testing, and now I think we're gonna see lots of development happen over the next week or so on the garden side. But thinking about that iterative design process where you have something that's sort of deliverable, and even if you don't finish by the time we get to the end of the individual projects, that you would have something to show like, this is what I've been doing. What we don't want is somebody to just plan and plan and plan, and then no action to happen. A big part of this, and actually I would say a large lesson that I would take away from making in a space like this, is the urgency is helpful. Even though it may feel like you're rushing into something, you want that experience as soon as you can get it. And so having the ability to get that experience to happen, oh, I should stop my share. Having that experience from making the first pass, from doing the first version of your design, and then using that to inform the second one is really helpful. There's a lot of trickiness to choosing a good one, and I want to absolutely help everybody choose a good path for themselves so we can have that discussion one-on-one for each one of you at any time and any moment. And I'm happy to support each of you as you're working on it. It's not like I wave as you go off into the sunset working on your project. I'm going to be here for backup and support. And so I want to make sure I'm just as invested in the fact that you'll have a great experience, and then you'll make something really cool as well, maybe not as invested, but I am right there alongside you. I suppose it's your project. And so I want to make sure that everybody is excited and successful and can find some movement forward. So it's definitely a good moment to pick a stretch goal, but it's also something that you got to keep in mind. You've got a limited time window. So thinking about bringing that all together makes it daunting. Usually choose something that you think is simpler than you might expect. It's easy to take a simple idea and jazz it up rather than choosing a complicated goal and then really having to have it all come together in one action at the end. That's the modular versus monolithic. It's easier to add in modules than it is to say, I want to build this thing that's going to take a composite body and then motors that move, and all of these pieces have to fall into line just right in order for it to work. A good resource, and I had, you know, a moment revisiting my past, but if we go to Fab Academy and pull this up, we are, I don't want to give the impression that we are this or that you would hit these sorts of marks, but in here they just, oh, yes. I can totally share my screen. Sharing this screen, do that, hit share, okay. And so in Fab Academy, you can look through like their index of different years. So if we head back to 2014, there's a list of students. And when you pull these up, these are when it finally loads. These are a whole collection of different projects that you can absolutely look at. They're usually well documented. So some of this is going to be, and even if they're well documented for us, it's still going, like, look at this thing. I don't know what that is. Tentacle. Sounds like fun. Even if they're well documented, there's still plenty of dynamics to get something like this to work, where it's probably not going to be just as straightforward as like, oh, those are instructions that I'm following, right? There's interpreting, making it make sense here. Some of their designs are going to have you milling circuit boards, and we're still not quite equipped for that. There's going to be different pieces where you might want to use an Arduino, where they might have done pieces that they had to make themselves. There's a whole range of different examples to look at. Oh yeah, JLC PCB is great for circuit boards if you can afford the like week of lead time, and it works great if you want to have your own circuit board for sure. I sure can. I'm gonna just go. Yeah, and so if we go to, it's just fabacademy.org, and if you go here into content, you can go down through all of this. This is going to have all of their, like, this is the year that I did it, 2017. And so if you dig around through here, at some point you can find mine, and you can find a whole host of other people that did this also. So they're depicted in different ways. Let's see, final projects. Another one that's fun to do here is to, oh, we can switch to thumbnails. Is it doing what I asked? Slowly. But you can totally just sort of pick through, scroll through, see what you like, what you don't like. If there's something that you really wanted to go after, there's some really cool examples here from all sorts of people from all around the world. And there's lots to be learned. Like, here's an automatic fish feeder. Remember, somebody had a system to grow mushrooms. Here's telescopes. Here's a exercise walking wheel. Look at how fun that is. but use PID control to stand upright. So there's all sorts of different things that you can learn and do and see that come along in here. And it's, you know, it's taking its time to load. That whole labs is offline. There's a whole bunch of things. And so somewhere here's like a fab cart. You know, there's a lot of different options. Here's like this is a fun one for photographers, a camera slider, where it's a linear axis. You can get a little bit of motion in your camera along and rotates it as you do. There's a ton of different ways that you can make all of this work and look at different example projects that you'd like to recreate or do or be inspired by. Here's a really nice herb garden. You know, there's all sorts of stuff. But lots of these things to look at, tons of examples across the board. And I would definitely recommend you roll through some of these, even if you're not going to build that, but just for some inspiration on what you might like, because these were specifically but this is like I think that was a molded, if I remember right, this was a molded bowl and a couple of motors to track a solar panel with the sun. You know, it's not just so that it would be like a potted plant, but it could charge a phone, right? It would turn and go with the sun. It used just enough motor to track the sun as it went on. So it's a neat, there's a whole bunch of neat examples in here that you can take a look at. But I love this designer. She did a really fun dog that would wag its tail faster if your hand was near it. You know, it doesn't have to be anything too like.
Such a dog is an interactive.
I think that this girl, I'm going to turn the volume off, but I think in the years since, she's been on the Lego TV show in Denmark. Yeah, there's a ton of different cool things that you can do. They don't have to be very practical. It doesn't have to be as sensible as a desk. It could be just sort of like a kitschy little thing. It doesn't have to do anything really. It can just be something that's there for fun, to enjoy. And this is, you know, a relative, you know, it's not a giant complicated thing. She's got motors and gears. It's just really elegant in her case. So there's a whole range of different ways that you can do a final project. And it's good to have your personality to come through with it, I think. But yeah, they had to do, for this, you had to do a 1-minute video about your project. That feels like a whole other goal to add on top, which I don't think we should go after. We should just have our projects and then have our show and tell session at the end. But there's the little dog. So there's a ton of different examples that you can take a look at, and you should what? Yeah, this video we'll find and share somewhere. Oh, I've lost my screen sharing. But yeah, that is, I feel like we should, oh.
I said I don't know what I'm doing. Okay.
Yeah. And so that's it. But it's tricky. So let's like talk our way through, look at some examples and see what looks like fun. All right, that's it. Let's build some stuff.